Hello all, my name is Jason Brenner. Today I am presenting the abstract titled Intravenous Flow Rates Using Commonly Available Venous Access Devices, a Prospective Observational In Vitro Study. The co-authors for this abstract are Dr. William Afterbach, Dr. Andrew Mastanduano, and Dr. Matthew Rivera. We are all affiliated with Northwell Health's Southside Hospital in Bayshore, New York. We have no conflicts of interest to report at this time. The inspiration for this abstract initially drew from an exploratory literature review regarding the effectiveness of different IV catheters throughout the practice of emergency medicine. We observed that Pascal's equation, which states that the flow rate of a fluid undergoing laminar flow is proportional to the tube radius to the fourth power and inversely proportional to the length of the tube, has seldom been scrutinized in its real-world applications within emergency medicine. Specifically, we set out to determine the flow rate of commonly available IV catheters and to determine the effects on flow rate of adding pressure via a manual pressure sleeve. We will also compare the manufacturer listed flow rates depicted in the image on screen with the experimentally determined values. To conduct our in vitro assessment, we created a setup very similar to the one on screen. We suspended a 1 liter bag of normal saline from an IV pole 85 centimeters above the ground. The saline bag was connected via needle-free IV tubing with the final 10 centimeters of the circuit maintained parallel to the floor. In certain trials, we engaged a manual pressure bag by inserting it above the IV bag in a similar setup. Our analyses included the following catheter sizes: 1.16 inch 24, 22, 20, 18, 16, and 14 gauge catheters, a 1.88 inch 20 gauge catheter, a 16, 18, 18 gauge triple lumen central venous catheter, a 15 millimeter and a 45 milliliter 15 gauge intraosseous needle, and a 9 French introducer catheter. We determined these IV and IO catheters to be the most commonly used among EM physicians. Based on prior research, we conducted 3 trials with each catheter. We measured our volume of output in a tiered container using a digital scale. The output was measured in grams and was later converted to milliliters. Total output was time for either 600 seconds or 300 seconds, depending on catheter size. Larger catheters were allowed to flow for just 300 seconds to prevent the confounding effect of diminished hydrostatic pressure resulting from a nearly emptied IV bag. In certain trials, pressure was added to the circuit using a manual pressure bag maintained at 300 millimeters of mercury. We also conducted a tubing alone trial to confirm that the tubing was not rate limiting. Our analyses included a 2x13 two-way ANOVA to explore the impact of application of pressure and IV size on flow rate. We also conducted post-hoc comparisons using the Turkey's Honest Significant Difference test. The graphic on screen depicts the flow rate of all the catheters tested under conditions of gravity and pressure. We observed a statistically significant interaction effect between IV size and pressure, with a p-value less than 0.001. There was also a statistically significant main effect for pressure, with a p-value less than 0.001. As is visible on this graphic, overall, the application of pressure increased flow rate by an average factor of 3.2. The range was 2.8 to 4.2. The effects of pressure application increased as catheter size and flow rate increased. On this slide, the graphic demonstrates that during the gravity trials, as IV diameter increased, IV flow rates were increasingly slower than manufacturer specifications. We found the range of this deficit to be from -17% to -77%. The other catheters were excluded from this analysis because official manufacturer specifications for flow rate were not readily available. As previously stated, we observed a statistically significant interaction effect between IV size and pressure, with the p-value less than 0.001. We also found a statistically significant interaction effect between IV size and pressure, with the p-value less than 0.001. However, with respect to the 2 most clinically used catheters, a normal 20 gauge catheter and its longer ultrasound guided counterpart, we did not find a significant difference in flow rate. Overall, the flow rate for the IV catheters ranged from 16.6 milliliters per minute in 24 gauge to 67.8 milliliters per minute in 14 gauge under gravity, and 46.6 milliliters per minute in 24 gauge, and 281.9 milliliters per minute in 14 gauge under pressure. Additionally, as IV diameter increased, IV flow rates were increasingly slower than manufacturer specifications. And lastly, application of pressure increased flow rate by an average factor of 3.2. In conclusion, increased catheter size and application of pressure were both independently associated with increased flow rates. We found no significant difference in flow rate between a normal 20 gauge and its ultrasound guided counterpart under gravity or pressure. Application of pressure nearly tripled the rate of volume infusion for all catheter sizes. Follow-up studies will involve both cadaveric models and an in vivo component to explore a more clinically accurate flow rate. Thank you.